Assalamu alaikum warahmatullahi wabarakatuh. Today we are going to start our second topic related to programmable logic controller PLC. Before we go into PLC, let us start with some fundamentals of control. Then we will move into the we will move into basically the what do you call it, relay logic. Sorry, the relay logic control, and then we will inshallah move into PLC basics. And then from next 2-3 lectures, will be all about PLC inshallah. So the control consists of monitoring the state of a critical parameter, detecting when it varies from the desired state and take action to restore it. So this is basically the concept of control. Control can be either discrete or analog, manual or automatic, periodic or continuous. The process variable is a parameter that is to be controlled. Example, temperature of a given space, pressure of a pumping system, so on and so forth. A device that measures the variables are called transducers or sensors. Example, like a pressure switch or a bimetallic strip temperature switch, and uh, encoder or force gauge. All these things are sensors that are used to carry out control actions. The set point is the desired value of the process variable, and error signal is the difference between the process variable and the set point. And this is the basis of any control action. The device that converts the control input output to control action is called the actuator. So let's talk about the discrete control. Discrete control deals with the system in which each element can exist only in certain defined state. Is basically another name of discrete control is on-off control. The device used to sense the system condition is discrete control are typically electrical switches with contacts or open that are open one when the variable is in one state and closed when the variable is in other state. So it's basically on-off control. So let's say this is a example of a discrete control. What we do here is basically a temperature sensor. There is a set point, and the position of the hand off auto switch will cause it to the motor starter to turn on and off this fan. So basically, if the uh, this is true, you are on all these things, and the set point, if they are not same, then it will cause it to turn on the system, the fan. So this is basically simple on-off control of the fan. It is not a continuous control. The fan speed is not continuously getting monitored and controlled. Rather, the fan is either turned on or off. On the other hand, analog control is a continuous control, so you continuously monitor a parameter and then you compare it with a set value, and if there is any discrepancies, the error signal will drive the control algorithm. For example, I think we have an example here also. So let's say basically a driver is driving a car, so that eyes are the basically the driver's vision, or the eyes are the sensors to see whether your car is in straight condition or deviate condition. You want to maintain it in straight condition, and then accordingly the driver will take action. Driver is the actuator controller, and it will control signal to the actuator steering mechanism. So you control the steering wheel, and accordingly the automobile is in the right path. So if you want to automate this car controlling system, you want to make a driverless car, so you have to bring a actuator to actuate the steering mechanism automatically. So this is how you can achieve an analog control system. So you can see it is a continuously operational control system, not just turn and on and off of the system. In cases of analog control, you have either proportional control proportional integral control and proportional integral and derivative control. Let me explain in a short explanation what is the difference between proportional integral, and proportional integral and derivative. Proportional control is pretty straightforward. When you have an error, you try to multiply this error signal with a gain value using a amplifier, inverting non-inverting amplifier. So you have the non-inverting amplifier, you can adjust the gain, and the error is multiplied with the gain and causes an voltage or an output which is proportional to the error signal, and that proportional to the error signal, and accordingly if the error is high, the actuation effort will be higher, and so on and so forth. If the error is low, actuation effort will be also low. But in an initial understanding, we can feel like, oh, that's good enough. Why do we have to have an I and D controller? There is a reason. The reason is, if you give a very high proportional controller value, then what will be the problem is that if a little bit of error signal will cause it to be very, because if you have a very high proportional gain to overcome a little error signal, then you have to give a very high gain. Okay, but sometimes it may happen that the sensor may give you false signal, so it is not really an error, it is a false error because of some noise issue. So what will happen is that small error will cause a huge correcting effort, and that will cause the system to be unstable, and your system will become very much vibratory. A little bit change in the error signal, maybe it is due to the noise, and it will cause the, if you give a very high kp value or the p value, then it will cause a very unstable system. But if you keep a low kp value, then small error cannot be overcome due to the limitations. So that is the problem. So you will always have a steady state error if your proportional constant value is low. But if you give a high proportional constant value, the problem is it will cause unnecessary vibration to the system. Now, to overcome this problem, let's talk about, instead of a multiplying factor, why not we just use an addition factor? Mean to say, we just add the error over time. So that is how the integral part comes. So when you have a kp value a certain level, then you will have an accumulative, you will have a steady state error because you cannot overcome this small error. But if you add up this error over time, that will have enough of strength, actuation strength, to overcome this error, but not too high a strength that will cause vibration to the system. So that's why you have PI controller. So many of the cases you are only stick to PI controller, but sometimes you may need a PID controller. PID control D, what it does is basically, sometimes you will see the if you have a set point, initially you will overshoot, your output will overshoot the set point and then come back, and then it will oscillate, and then it will output will be settle down around the set point. So to how fast you want to achieve this state of steady state condition depends on the D value. So if you have a very high D value, your system will be sluggish in response, and basically it will cause to be sluggish in response. Fast in response. If you have a low D value, it will be sluggish in response. But if you have a high D value, another problem is you may cause higher overshoot. So based on the design criteria, you can set what is the value of P, I, and D. Based on that, you can decide how to control PID. Now, in this course, we are not going to discuss too much on the analog control. Our PLC, we will be focusing only mostly on the sequence control or on-off type of control. But before we move into PLC, let us talk about our relay logic control system. So in various machines, you may have seen this type of relay board. This is called relay board. If you open the back end of the machine, in various machine, you will see this type of relay board. So this is called relays. It can be DC operated or it can be AC operated as well. Now, so a relay looks like this. So the symbol is, this is the symbol, and if you have a normally closed connection, it will be this. If it is normally open connection, it will be like open. So what it does is basically, uh, let's say this is a AC contactor or relay. So if you energize this coil with 120 volt AC, this will basically cause this electromagnet to pull down these switches in which are spring loaded. So once these switches are closed, then current can flow through this. So this is called normally open type switch. Normally it is open, but when the coil is energized, it causes this switch to be closed. So you can have a solid state relay as well, which is coupled with an optotriac. So you have a solid state relay, very low voltage, usually 5 voltage. So if your voltage, if your switch is closed, the voltage will cause this LED. Internally, they have an LED. So this LED to be turned on this side, and then optotriac will cause the other side to carry the current. It will be shortened, and the other side will carry the current as well. So this is how you can separate the input and output devices. So these are some symbols of limit switch, momentary contact, and pressure switch, manual switch. Remember, in PLC, we will encounter these two terminology very often. One is called momentary contact, another is called maintain contact. So momentary contact, you can think of a doorbell switch, which is spring loaded. So if you press the doorbell, as long as you hold the doorbell pressed with your fingertip, then the contact is closed. But if you remove your hand with your fingertip from the doorbell, the contact will become open again. So this is we call momentary contact. We need to say as long as the moment you hold this switch. But maintain contact means it's like a light switch in your electric light switch. If you turn it on, unless you give an opposite signal, it will remain as on. So this is the case. You have pressure, but mostly you will be using this momentary contact and manual switch. So if those switches has normally closed condition, then you will have, it is, the symbol is closed, meaning to say in normal condition it will carry current. If you press, then it will be disconnecting the circuit from the current source or the voltage source. Output, usually we will be using all the output as simple lamp or solenoid coil and all these things. These have different symbols, but in later you will see all these symbols will be generalized into only a bracket type of symbol. Okay, now how does the relay work? So in the relay, if you have, you can see it's a spring loaded switch inside. So once this electromagnet is activated using some voltage. So basically, if you have some voltage, it will cause this electromagnet to be activated. Then this cantilever switch will be pulled down. Once it is pulled down, this will be connected to this normally open contact. So this will become closed, and then normally closed will become open because this will be pulled down. So normally closed will become open. So this is how the system works, the normally closed and normally open. Normally closed means in if you don't energize the switch, it will carry current. Normally open means once you energize the switch through electromagnet contact, then it will start to carry current. Let us pause here for a while, then we come back again. Okay, now let's move on to the next slide. Um, let's say if you energize this coil, normally closed will become open in that case. Normally open will become closed. So this is the example of the system control relay. Okay, so now when this is called a typical ladder diagram. Why is it called a ladder diagram? Because you can see it looks like a ladder. Ladder means you have two columns and in between you have horizontal bars to climb up something to fit your bulb on the ceiling. You use ladder. So that's why it is called ladder diagram. In ladder diagram, you will have two vertical line and many horizontal line. So this horizontal line is called rung, R-U-N-G, rung, R-U-N-G, rung. So each rung, now let's say on the left side of the ladder is called high voltage, on the right side of the ladder is called low voltage. So the current flows from the high voltage to the low voltage. Though we don't mention it explicitly, but this is how it is understood. Now, if we have two switches in series and then you turn out, it is basically an AND logic. So you press this PB1, you press this LS2, then only the solenoid will be activated. This is what it means by this ladder diagram. On the other hand, if you have an OR condition, so you will have two switches in parallel. So either this switch or this switch, any of one of them is closed, the rung, R-U-N-G, rung will carry current and it will energize CR6 solenoid or CR6 coil, control relay coil. So if both of them are not turned on, then only it will not be carrying any current. Okay, let's now discuss about this relay logic diagram for a one-shot uh, one-shot cylinder. So what we do here is basically you have a pneumatic cylinder. If you see this cylinder has a two input port, if the air goes here and the air exits from the right side, then the cylinder will go from left to right. On the other hand, if the air goes into the right chamber and exited from the left chamber, then the cylinder will move from the right to left. So what we want to do is basically we want to press a PB1 switch and the cylinder will go all the way to hit something and it will hit this limit switch and at the end, and once the limit switch is hit, it will immediately come back to its original position. That is what is desired. This is called one-shot cylinder control. So let's see how it can be operated. Given the scenario, how can we achieve this solution? So what happened here is explained in a step-by-step process. At first the switch was open. So if you press the switch, this line will carry the current, as can be shown here. Once this coil is carrying the current, it will turn on this normally open switch to be closed. And this open switch also will be closed. So this switch is closed, this switch is closed. So this is now also carrying current, this is also carrying current. So the solenoid will be activated, the solenoid will be activated, so the valve will be switched on. So that will cause air to be going in, this air to be exited from here. And hence this piston will be moving forward. Now interesting, you don't have to hold and press this PB1 because this parallel line is carrying the current as well. This is called the latch. So because of this latch, it will also carry the current and it will hold the switch. So hence you don't have to hold this switch anymore. So this will cause this control relay to be energized and hence still this piston will move forward. Now once this piston move forward and as soon as it hits the LS1 which is currently normally closed, that will cause something. So once it move forward and still it is moving forward, and in the next slide, as soon as it hits this LS1, this will cause this normally closed switch to become open, and hence this latch this latch path will no longer carry the current, and CR1 will be de-energized. And as soon as it is de-energized, meaning to say this CR1A will be open, CR1B will also be open. So these are open, and because of that, this cylinder will start to move back because of the solenoid valve will be switched off, and this will cause this air to be exited from here and entry from here. So this right chamber will have the air, and the left chamber air will be exited out. So that will cause this cylinder to move backward. So this is how the system works. And this is all done by control relay switches. Now, what is the drawbacks of any relay based control circuit? As you can see, this is a hardwired system. So you don't have any software, rather you have all actual wire connecting each other, and it is sometimes become very messy and complex. And if there is any change in operation, you have to rewire all the things. You cannot just update the software. And finally, it is very difficult with this messy system to do any sort of troubleshooting. So these are the problem of any relay-based control system. To overcome this, then PLC was introduced and invented. So it is less wiring and basically easier to faster make changes, and wiring between device and relay contacts are done with PLC programming. No longer wiring is required. It is done by programming. And troubleshooting aids make programming easier and reduce downtime, and reliable components make these likely to operate for years before any failure occurs. So the origin of the PLC. It was first developed in 1960s, cost dropped significantly by 1980, now used in many industrial design. The primary goal is to eliminate the high cost associated with inflexible relay control system. So what is a programmable logic controller, PLC? This is a digitally operating electronic apparatus. So it's an electronic apparatus, digitally operating, which uses a programming memory for the internal storage of instructions and implements a specific functions such as logic, sequencing, timing, counting, arithmetic, so on and so forth for various types of machine and processors. So basically, the key point takeaway is it is a digital system. No longer it is an analog system, it's a digital system. So as soon as you say PLC based control, means it's a digital control system, and it takes many various input. It has a memory structure which we will show you later on, and this memory basically stores the programming instructions, and it executes the commands as per the input status. So leading brands of PLCs are Allen-Bradley from America. Then you have Texas Instruments, General Electric, so on and so forth. American brand, European brand Siemens is very popular. You have Festo is also popular. Others are not so popular. Japanese Omron is the most popular in Malaysia. Fanuc is also popular. Mitsubishi PLC is also popular. So what we are going to discuss in this course, Allen-Bradley PLC sequencing. So we will be using the syntax of Allen-Bradley PLC. Later, I will ask you to download a software that you can simulate the PLC instruction, which we'll be using in this course. Okay, where are the areas of application? You can see manufacturing, food and beverage, and everywhere PLC are being used. Oil and gas, and other places PLC are used. PLC size is defined by the memory size or input size, input output size. When you have only 128 IOs and 2 kilobytes of memory, this is considered small PLC. Mid-range PLC are 2048 IOs and 32 kilobytes, whereas large one can go up to 8000 IOs and 750 kilobytes of size. Allen-Bradley PLC structure is mostly expandable, so you can start with a small and then you can slowly expand it. So major components of a common PLC. Sorry for the sound. So you have a central processing unit like computer. Then you have a power supply which gives power to the processor. You have programming device. Now this programming device previously in old days it is a separate device. Now it is a computer basically. You plug in PLC through USB port or LAN port with the computer, and it communicates with the processor to give the instructions and to burn to basically store the programming uh, whatever instructions onto the processor. And then you have IO modules. This IO module connects with the sensors, switches, and all these things to get the input from the environment, and it gives to the processor, and the processor gives output to the and this is for the sensor through input module to the processor, and processor gives output module to the actuators, solenoids, actuators, contacts. So this is how the PLC works. It's more or less like a computer. IO module is basically DC IO module. You have input from the devices, and then you have a current limiting resistor. The current limiting resistor is to limit the current that is going into the system to a safe value. And then you have an isolator, opto isolator. It is needed to prevent any problem in the input side that will not hamper the output side. So this isolator ensures that any voltage up, down, or transient would not damage the controller side, mean to say the processor side. And then it goes to the processor. You have some buffer, filtering, hysteresis circuit, and then the signal goes to the processor. Same for the case of output module. Sorry, for AC module, you have extra thing, which is a rectifier resistor network, rectifier circuit, because you have to convert your AC into DC signal. And then opto-isolator, buffer, and finally processor. So this is called opto-isolator. This is also an opto-isolator. You can see how opto-isolator is causing the input to be connected to the through PLC module. So this is the isolated unit inside it. So if anything happens, this LED will be burned. So this side of the circuit, will be still saved. And for rectifier circuit, you know, this is a 4 diode rectifier circuit, a full bridge rectifier, and then you have the isolator unit, opto isolator unit. This is the rectifier and this is the isolator. Now for the case of DC to AC module, so you have from processor, basically you have TTL circuits, and then you have opto isolator, and then it goes to the amplifier, and finally it goes to the output devices to actuate the contactor, relay, actuate the contactor, or the for example the solenoid valves and all these things. So this previously I showed you from the input device how it goes into the processor. Now from the processor you get the output on and off condition, and that will go through the opto isolator, and finally it will go amplifier to turn on and off the actuated devices. Now there are various types of output. Mostly you have pilot duty output. These typically used as high current electromagnetic loads like solenoid relays and also as such. You have general purpose IO, which is mostly we will be using this, and you have discrete input and general purpose output. These are the two things that we will be mostly using in our whole lecture. Discrete means it is on off conditions, so you have only input conditions on and off. You will not have any input condition, continuous analog input. Some PLC does support this, but we will not be considering this as for our part of syllabus. Analog IOs, as I have mentioned, we are not going to discuss analog IOs for our discussion, but bear it in mind, PLC nowadays can handle analog IOs as well. Special purpose IO, you can, this is for very special high frequency output. If you want to, or high frequency input, if you want to deal with, you may have to use special purpose IOs. So these are the inputs like input push buttons or special sensors like light sensors, which digital type of sensor. And then output is a contactor, motor, contactor to turn on the motor or the lamp, so on and so forth. Processor is basically like other processor in computer system. Is a central processor unit, and it basically has a memory system which has system memory and application memory. So how this is how the memory map can be considered. System memory basically includes all the executive composed preliminary permanently stored programs. So when you store the program, it is stored in a ROM, read-only memory. So it is basically permanently uh, stored. Even if you turn off the power, the program remains there unless you erase that program. Whereas in the RAM, basically you have uh, random access memory is like computer random access memory, memories and volatile memory RAM. You have random access memory. You have non-volatile memory ROM, read-only memory, where you store the program. Okay, the main one of the important things that you have to understand for PLC how this sequence works. PLC is a sequential process, so it does the read the input. First, it scans whatever is the input. Then it evaluates the program that what if these inputs are true, what have to do based on the program that is stored in the system. And then it will do some internal work, diagnostics and communication related. And then it will update the output. So this is the output will be updated. And then it will come back to this phase. So now in between, if there is any change in the input, there will not be reflected in your output. So this is the limitations of it. It's not parallel processing, it's a sequential processing thing. As I have mentioned, it is mentioned it in textual format. Okay. As soon as the phase 4 is coming, the entire cycle begins again with the phase 1. So, so basically you have to understand what is the scan time based on how fast is you want your PLC to run. So to time to take a single scan, it may vary from 1 millisecond to 100 millisecond. This is an old note. Maybe nowadays you may have less than 1 millisecond or something as well. PLC communications can be various types of communication. It can be through RS-232, LAN, or it can be via USB, and you can using LAN port as well. You can communicate with the PLC module. That's all. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.